Okay, first I'm so happy with this class. You guys, both the online and in person, just did phenomenally on this exam. And it wasn't any easier than exams I've given in the past at all. So I don't know what's going on, but you guys really did a great job, and I'm delighted. I don't know what else to say. It's just fantastic. I'm very encouraged, and so everybody should be, and I hope you do as well in the final. So this is great news for everyone, and I'm really happy about it. I hope you are too. So I don't really need to go over many problems because people did so well on them, but just check. This time there was only one version, so we can just go through this together. Just make sure it's graded correctly, and I'll give you a few minutes at the end to, let's see, a few minutes at the end if yours wasn't graded correctly or if you have any questions. This, on page 1, part D, some people forgot how to do this and C and D. But the rest of it, people did very well on this page. Next page. Well, the chart, of course, people practiced and did extremely well. And this question, too, all these questions, page 2 was a phenomenal page, was the best page in the exam. And even, you hadn't seen some of these questions before, but you still did excellent on them. Okay, and now stop me if you have any questions on any of it. This page, there were some careless errors, but apart from careless errors, and we tried to give continued error here, like if you this is the only, some people just got messed up because there was this big long space here, and they somehow filled that in and got something messed up here, but it was worth 1 point for each blank and with a continued error. So if you got, for example, this one wrong or misplaced it, you should, as long as you did the other ones, you were okay, as long as your logic was correct. A lot of people didn't show work, so you should have gotten a point or a half a point off maybe if you didn't show work, because I said to show work, even though I know you knew how to do it, especially, if you make an error and then you don't show work, we can't give you partial credit, obviously. Okay, now, here was a big problem, this last one, M. The two-sided versus the one-sided. For the 95% confidence interval, you're taking it's equivalent to that's 5% out, 95% in the middle and 5% in the tails. That's equivalent to a two-sided less than 5%. And a one-sided, just counting one of those tails. Next page. This page was I was surprised you did so well. I mean, this was a very straightforward page, but it wasn't easy. And so I guess most of the problems came on this page, but people generally did pretty well in here. So remember, this equation here won't give you how the estimated probability of survival changes when your diameter changes, because look at the curve. It varies depending on, here it's very gradual, here it's very steep, and here it's gradual again. So this is what this one looked like. And impressive scores all around. So I guess if you have any questions, I'll let you out a little early and you can come ask me. So let's move on to finish up what we're doing. I just want to direct you to the calendar for just 1 minute, and let's see what we have up here. Okay, so let's go to the calendar, and let's look at what's due. All right, so here we are, and you have this final conflict sign-up that's due Friday, as well as the bonus survey 5. Then this homework is already posted. That's your final homework. And the bonus R problem 5 has also been posted. Some of you, That's due Wednesday. Wait a minute, we have these 2 homeworks due. There is no homework 22. So there's just practice problems. There's no homework 22 due. I'll have to erase that. What there is instead is on Lon Kappa, there's a practice final, and there's a bunch of practice problems that were homework 22, and I just changed them into practice problems because I want you to get started on them right away and practice with them so that you can ace the final the way you did it, exam 3. So I turned that homework 22 into just practice problems. You'll find it on Lon Kappa under practice final and practice non-parametric problems. So you can do it there. And that way you can do it repeated times and start at the end of this class. You'll have all the material we're going to cover by the end of this class. And then you can just start studying. Okay? All right, so that's what's... so you know what to do, and of course I'll send you your usual email telling you with more explicit instructions about how to study for the final and where to go and what to do and so forth. But let's just finish up the material that we have to do for today. So let's do that now. And so, any questions? All right. Now, let's look where we are. We're at this. Okay, so looking at this on, where are we? On this on page 211 right now, jumping ahead 2 pages just so you can see where we're going, what we've done so far. All right, so we have these 3 non-parametric tests, and so far we've only covered this one, the WMW. The Ranksum or U statistics, and that's the parametric equivalent of the 2-sample t-test. So what are we going to do next? We're going to look at the non-parametric equivalent of comparing 3 or more sample means of ANOVA. And that's what we're going to do today, the Crisco Wallace test, as well as the non-parametric equivalent to the correlation coefficient called the Spearman rank order correlation coefficient. So these are both very short and simple, and that's what we're going to do now. So the first one, right here, chapter 41, on page 207, is we're comparing, it's called the Crisco Wallace test, and it's to compare 3 or more groups, the means of 3 or more groups. It's the non-parametric version of ANOVA, okay? And again, it has the advantage of not having the assumptions about the underlying normal populations. And it's basically, it's very, very similar to what you've been doing. You combine, instead of combining 2 groups, you combine all the groups into one ordered list. That's what we do first, from smallest to largest. And again, we assign each observation from 1 to n. Let's say you have n observations. You assign each one an integer from 1 to n. That's no different than what we did last time. And then the only difference is our test statistic. We are going to approximate it not with a z, but because we have 3 groups, we can't boil down the differences between them to a single sign number like we can using it with 2 groups. So what do? We're not going to use a z-test. We're going to use a chi-squared test. Not an f-test, because remember, once we change all our observations, whatever numbers they are, to integers between 1 and n, then we're going to know we'll know the distribution of those numbers. It's just uniform, and they'll vary quickly. It's like a chi-square test. We'll know it will be like the sum of squared normal distributions, which is a chi-square test. So we're going to approximate it with a chi-square, and that's it. So let's do it. All right. So I think you know the routine now. So let's just highlight this. We're doing a chi-square test on this. And all right, so let's just extend our former example. Now we have 3 forms of the final exam. And I'm going to randomly distribute it to 16 students, let's say. And the null, of course we randomly distribute it, and the null is that all of the forms are the same, and not only the same means, but the same level of difficulty. All right, so now for each group. So now were all three versions of the final equally difficult for all types of students? Here are the scores. All right, we've got the scores, and since you've got a lot of groups here, what I did is I just ordered all the numbers. The smallest score was 10. That was the worst score, and the best was 100, and here's all 16 of them, and I ranked them. Now, there was a tie here, 2 70s, so instead of 5 and 6, we gave them the same, 5.5, and that's, here they are. So we'll just have to look, and we see, okay, 10 is 1, right? 60 is 4, 70 is 5.5, etc. 80 is 8, and 116. And we'll do that for all of them, right? So here, 70, 50 is, 3, then we have 5.5, and then we have 9, and 10, and 13. And here we have 20, 75, 86, 90 is 12, and 98. Okay, so we have that. And as usual, what we're going to do then is these are the numbers. We're just going to add them all up. So the sum here, adding those up, is equal to 34.5. And the sum here, adding up those 1, 2, 3, 4, 5 numbers, is 40.5. And the sum here of these 6 numbers is 61. Okay. So these are our observed rank sums, right? And we should check that 34.5 plus 40.5 plus 61 equals what? Sums to 1. Remember, the sum of numbers between 1 and n is going to be n times n plus 1 over 2. So in this case, it's going to be 16 times 17 over 2, which is 136. So we should make sure that these numbers sum to 136. And they do. So we didn't make a mistake. All right. Now, we're going to compute the expected sum, expected rank sum for each group. And it's no different than before. What is it going to be? It's going to be right here. This is the size of the sample, right? N1 times, we should maybe write this down. So this is going to be, we're going to do this for each one of these. But what is n sub I, and what do all these mean? So n is equal to the total number of observations. It's the same as before, but you might have forgotten. And then what do we have here? N sub I is equal to the number of observations in each group. In group I. That's because they have different. They can have different numbers of observations. Like this one, n for A is 5, n for B is also 5, and n for C is 6. All right, and then let's to make sense of this, so you don't, because you are not going to be given this on the final. You should know this. What's n plus 1 over 2? Let's think about it. N plus 1 over 2 is equal to the mean, the middle of the group. It's the mean of all n observations. It's the average of all n observations. It's the average of the numbers 1 through n. That's what it is, remember? So in this case, what is it? It's 8.5. It's this part right here. So this part right here, that's the average. And when we sum up all the numbers, all 16, you can think of when you randomly distribute these integers between 1 and 16, wouldn't you expect to get about the average in each group? We wouldn't expect to get more or less if they're randomly distributed. So that's why you'd expect to get right here, this part of it, you'd expect to get the average in each group, and then you multiply by the group number. So here we get 42.5. That's what we'd expect to get. And we got, because we have 5 times 8.5 here, and here we have 5 times 8.5 again. That's n times the average for that group. So you'd expect that one to be the same, wouldn't you? But this one has 6 observations in it, so wouldn't you expect this one to be bigger? When we, expect on the average that each number is the average of the whole group, and then you have 6 observations here. So that's, you're summing them up, so this, since it has 6, is going to be bigger. Okay, so there's our expected. And what else should we do? Maybe I should just write this. So right here, that's the number in each group, the number of observation in group, and this part is the average of all the numbers. If you think of it that way, it's really easy to remember. It's the same formula as this one, just applied to the groups. It's the same as this one, just applied to the groups. Okay, and now you have this chi-square dis. Any questions so far? Okay, and now remember what a chi-square distribution, what the statistics is. It's the, let's look at this. What is this? It's the sum of the observed rank sums minus the expected ones squared over what usually you have for a chi-square. Those of you who've taken Stat 100 or AP Stats probably learned it as the sum of the observed minus the expected over the expected. So why do we have a little n1 there, and what's this? Well, it's really the expected variance. That's really what it is. And the expected variance, if you remember, is going to be, this is exactly, the variance is just the standard deviation, or the standard error squared, right? And so here, that's exactly what this is, simplified. If you recall, first of all, this is going to be given to you on the final, this part, this whole formula. So this is going to be given to you. And just to make sense of this part of it, if you want, let me pull out a piece of paper here. If you want to make sense of this part of it, what we're going to, you could just rewrite this as what? The sum from I equals 1 to G. You have 3 groups, and for each group you're just going to take its observed rank. Like, for example, sum, like this is this one minus that one, for example. The observed rank sum minus the expected rank sum. So this is the observed rank sum minus the expected rank sum. I don't know why I put parentheses there, sorry. Squared over. And now I'm just going to rewrite this. It's really over the expected variance. But I'll just rewrite this in a way that's more familiar, I guess. And so if you, I just want to rewrite it as, let me show you what I'm doing, so what's motivating this. I just want to show you it's the same thing as what we had before, which is this. That's standard error, right? If you square that standard error, you'll get the variance. So I just want to put that in the denominator so you can see it's the same thing. You don't have to pay attention to this, by the way. This is just if you're interested. So let's go back to where we were. Right here. And you can just see it's just arithmetic, right? If I put this, so I'm going to put the square root squared, and then I just want it to look like that other square root formula, which looked like what? It had a 12 in the denominator, right? And now you have n1, n sub I there, and here you can just rewrite it as n times n plus 1 squared. So that's the observed minus the expected over the expected variance, and that's a chi-square statistic. And a bunch of you are interested in where this 12 came from, so I'm going to just insert a little explanation inside the video. I think that would be the simplest thing to do, so I don't take up a lot of time here. Okay? All right. So I'll post it in the video. Questions? But this is given to you. All right. So you know that, okay, so this is a standard error. Think of it as, let's just compute it as a variance. So if we squared this, what is think of a standard error or a standard deviation squared. Basically, I'm going to do the standard deviation squared of numbers between 0 and n. And that's where this 12 comes from, and then change it to a standard error. So if we take the standard deviation squared, that's going to be the sum from I equals 0 to capital N. So if you went the numbers between 0 and 10 or 0 and 100, whatever, you know that you take your deviations and subtract off the average, right? Those are the deviations, and we sum them all up. We just sum them all up without squaring, you get 0. So you squared them, and then you divide by n. And take the square root if you want to do the standard deviation. That's just our formula for standard deviation. All right, so now you can simplify that and just break it up into two parts, and you can say, okay, you have the sum from I equals 0 to n of x sub I squared over n, and this is just algebra, minus x bar squared. And that's a formula, the computational formula that a lot of people learn for the standard deviation. So now, what are we going to do? Now, what I'm going to do is just, let's say, the easiest way to see this is if you just took the integral of this between 0 and n, and that's where you could see that the 12 comes, where the 12 comes from. So if we just took the integral, right, from 0 to n of x squared over n, and then this is just this constant. If you add up the numbers between 0 and n, like between 0 and 10, what's the middle number? What's the mean? It's just going to be n over 2, right? 0 and 10, 5's the middle number, right? If you did it between 0 and 100, 50 is the middle number. It's just n over 2. So this is just minus n over 2, and then it's squared, right? That's all that is. And so now I'm just going to integrate this. So when you integrate x squared over n, you're going to get x cubed over 3n, and you're just going to evaluate it between 0 and n. And this is just what? N squared over 4, right? So that's what you have there. And so now, what will you get? Put an n in for x, and you get n cubed over 3n. So simplify that, and you get n cubed over 3n. So you have n squared over 3. And you put a 0 in for x, and you get 0 minus n squared over 4. And find your common denominator, and ta-da, there's your 12. That 12 pops up all the time when you're looking at the integral of numbers between 0 and n. I mean the variance. Okay, so that's the idea there given to you. All right, so now let's just do it. Oh, distribute as a chi-square with how many degrees of freedom? This you should know because chi-squares is going to be, as usual, it's going to be the degrees of freedom, as usual, are going to be the number of groups minus 1. So it's going to be 3 minus 1, which is equal to 2. So that's the degrees of freedom right there. Number of groups minus 1, which is what it always is. All right, so now it's just computing it. So this is our H statistic, right? And our H statistic is going to be what? It's just 12 over n is 16 times 17. And then what are we going to do? So we're just taking the observed minus the expected over the size of each group. So it's going to be for the expected for here is 42.5, and the observed is 34.5, minus something else over 5 squared, plus something else over squared, plus something else over 6 squared. So what should I put in there? It's just your observed minus your expected. And this makes sense because the closer you get to the expected, look, what if you got exactly the expected? Your H statistic would be 0. So the bigger your H statistic is, the more evidence there is against the null. The more extreme you are from what you're expected, the bigger your statistic is, as usual. Okay, so now what are we going to do? What are our observed minus expected for the next one? It's just 40.5 minus 42.5. And our last one is just what? 61 minus 51. And that's it. So let's do it. 12 over 16 times 17. Let me just show you what these differences are, because they're a nice way to check. When you say 34.5 minus 42.5, what do you get? You get negative 8. And here you get what? Negative 2. And here you get 61 minus 51 is 10. So this is just a nice, with all this arithmetic, I just want to show you that, remember, the reason we square these to begin with is because if we didn't square them, what would they add up to? They have to add up to 0. Negative 8 plus negative 2 is 10. Negative 10 plus 10 is 0. So that is the whole reason when we have these, we have to square them when we look at these differences. Otherwise, we'd get the same answer every time, 0. And so that's what we're doing. So just that's nice to check if you're doing it. And when I did this, I got 1.344. So what are we going to do? We're going to compare that to what? We'll compare to, we have to compare to the critical value of chi-squared critical value, chi-squared critical, at degrees of freedom 2, at whatever we want. The chart that you'll have on the final is at alpha equals 0.05, so let's use that one. All right, and that's a standard one. So I think, let's just look in the back of the book and see what it is. So it is, with 2 degrees of freedom, at 5%, 5.99. So 5.99, think about 5% is beyond 5.99, and our chi-squared is way up here at 1 point something. So our p-value is huge. This is an everyday occurrence it's very consistent with the null. It's nothing surprising going on here. It's going to happen all the time to have a chi-square up here. Remember, the mean of the chi-square is its degrees of freedom, so it's about 2 in this case. So we could tell that's not going to be significant just by looking at it. Okay? So we'll say compare it to this, which is equal to 5.99. And the picture is going to look something like what? Something like this, where it keeps going. And our critical value that we have, this is 5.99. And our chi-square is this. That's what we're comparing. So that is like way up here. So we're comparing those two. So our p-value is like 50% or something or more, and this is 5%. We're nowhere close to rejecting the null. Okay? So it's way less than 5.99, so we cannot reject the null. If we wanted to find the exact p-value, we could look on the p-value calculator. I found it, and our p was equal to 51%. The area all the way there was 51%. This is RP was 51%, and this business right here is 5%. That little tail. Any questions on that? All right, so that's pretty easy. And we just have one more page left to do, right? Let's see. Yeah. Okay. And then we'll do some clicker questions that are review on just some questions, things like you might see on the exam, just a few, and then you can stay and do your homework if you want. All right. Because we're going to have a review next class. We'll have our review for the final. When you've had a chance to study the final, we'll have a real serious review. Okay, so chapter 42, the Spearman rank order correlation coefficient. Again, what are we doing here? We are going to, the correlation coefficient. We're going to look at, we're just doing this correlation coefficient, looking at whether two sets of numbers are correlated. These are the pairs, and we could graph them, etc., and see how closely they follow a line. But what are we going to do here? It's the non-parametric version of the regular correlation coefficient R. It's computed exactly like the regular correlation coefficient R, except you change all these numbers to, what do you think? What do you think you do? You change them to ranks. All right. So we can do, that's all it is. And then so if you have, how many pairs of numbers do we have? 1, 2, 3, 4, 5, 6, 7. So these numbers are all going to be changed to integers between 1 and 7, every one of these. We're going to rank the x's and rank the y's and see how closely they match up. That's all we're going to do. And then it's super easy. All right? So change to ranks. I already put the x's in order here. I just ordered them here. So this is the first number on the list, second, third, fourth, fifth, sixth, and seventh. So I listed them here. And now the y values are also going to be integers 1 through 7. They're just going to be in a different order. And the null is that they're just in scrambled order. And then we're just going to compute a correlation coefficient based on these. And it's easy to do. It will follow a z distribution as long as there's enough points, like 7 or more, because these numbers are so evenly distributed. They're just uniform distributions of x's and y's, so it's going to approach normality very, very quickly. It's the same idea. So now we just have to look at the, all right, so what should we do? What's our lowest y value? We're just looking at the second numbers here. What is it 40 is our lowest? Is that the lowest? That's the second lowest. First, second. What's 45? What's that? What comes next? Is this the third lowest right here? 61. What's bigger than 61? This one. So that's 4. And then what do we have left? That's 5. And then we only 6 and 7. All right. So those are our pairs. And now it's just an easy problem. We can even do it by hand. Might as well, so you remember how to do a correlation coefficient, which is something you should know how to do. So we'll just put these here. So So we have 1, 2, 2, 1, 3, 4, 4, 3, 5, 7, 6, 5, and 7, 6. We could plot them, and they look pretty close to a line. See how they're pretty, you could plot them if you want. But how do we figure out a correlation coefficient? We have to change both x's and y's to z-scores. Then take the product of the z-scores and then take the average of the products. Remember? And that's what we're going to do here. So the Spearman rank correlation coefficient is just like the regular correlation coefficient, just after you change all the numbers to ranks. It's computed the same way. All right, so the regular correlation coefficient, remember what we do, we're just going to take the sum of those products of the z-scores, zx times zy, and then just take the average of them. And the Spearman is doing the same exact thing once you put them into integers, once you just rank them. That's it. So this is the average here. X bar is equal to 4 and y bar is equal to 4. And I picked these numbers 1 through 7. The standard deviation is easy to compute, and it's 2. So I'll just tell you that. This is 2. And then you know how to find the z-score. It's just going to be the value minus the average over the standard deviation. So what's 1? 1 minus 4. It's 3 below the average. Then we divide by the standard deviation, and we get negative 3/2. Right? And this 2 minus 4 over 2 is going to be negative 1. 3 minus 4 over 2 is going to be negative 1/2. That'll be 0. And then it's symmetrical. 5 minus 4 is 1 divided by 2. 2 divided by 2, and 7 minus 4 is 3 divided by 2. So those are the numbers. And if we add them together, we sum these all up just to check. They have to add to 0. Let's just make sure, and they do. Right? All right, now we'll just do the same thing they're the same numbers. These are just put in a different order. So now we're just saying what? 2 minus 4 over 2. That's negative 1. This is negative 3/2. This is right at the average. This is 1 below the average. This is 3 above the average. This is 2 above the average. And this is, 1 above the average. 5 minus 4. And this is 2 above the average. And these sum to 0 too. Okay, so now we're done with that. And then we just multiply these together. So we get what? 1.5, 1.5, 0, 0, 0.75, and there we have 0.5 and 1.5. Okay, and then we'll add them all together. We get 5.75 divided by 7, which is 0.84. And that is our R. And you might look at that and say, whoa, it has to be significant. That's a huge R, but because R can only go as high as 1, right? Or as low as negative 1, so it's almost, but we only have 7 points, so it's not as significant as you might think. So let's just do the test. So our null is that it's 0, the population correlation is 0, and the alternative is two-sided because we didn't make any predictions ahead of time which direction it would be, whether it would be positive or negative. So for 7 or more pairs, the distribution of R under the null is approximately normal because these numbers are so evenly distributed. They reach normal. This is an average, and like any average, by the central limit theorem, that is, it's going to, if n is large enough, the sum, the average, and the average of random draws will look like the normal curve. And we just have such a nice even distribution, it reaches close to normality early. So it's obviously not normal because the normal curve goes forever, and this correlation coefficient only goes between -1 and 1, and there are only a limited number of possibilities. But we can approximate it with the normal curve. All right. But the nice thing, too, is that the expected value is 0. We'd expect 0, both as a z-score, right, and as a correlation, a Spearman correlation. We'd expect it to be 0. And as a z-score, we have 1, 2, 3, -1, -2, and -3. And the standard error is an easier formula than our usual one. Why? Because we know the standard deviations. Do you remember what our usual one was? They were doing our usual standard error for the correlation coefficient was the square root of 1 minus r squared over the square root of n minus 2. But now this is easier, much easier formula. And r squared's 0, and we're not approximating the standard deviation. We know it, so we don't have to subtract off. It's more like estimating a mean when you just divide by n minus 1, not by n minus 2, because we know the standard deviation. We know these numbers now. Okay, so now what do we do? So this right here will also, is this going to be given to you? Yes. You just, this is going to be given too. It will just mix you up too much if you have too much to remember. So if you want to know what's going to be given to you, you can just look right here, and it's going to be the same, and there you see it. Okay? It's going to look like that. So it's all the formulas you've already been given, which were these two, and these are the new ones. So that's what it will be like on your final. All right. So that's given, and so all we have to do is observe minus expected. Well, we observed 0.84. We expect 0. And now, over this easy, over 1 over what? The square root of n minus 1 is 6. Square root of 6. So this is 2.05. All right, so now what do we do? 2.05. So that is right here, and that's what corresponds to 0.84. Okay? And between 2.05 and negative 2.05 is what? About 2, a little more than 2, is about 96%. We'll put that in the middle. So our p-value for the two-sided, it's two-sided, see, because it's two-sided. It's going to have to include both tails. And so p is equal to 4%. So it is, we do reject the null and conclude there's very strong evidence that the correlation in the whole population is not equal to 0. Okay, we are done. Let's see. So now let me just show you so these practice problems are what was going to be your homework, but I decided to post them as just problems you can practice on Lon Kappa, so they're up now. Your homework's up now. Your bonus is up now. You can finish all that easily. You can finish it today, and then you have this final here with the key, and then you have a randomized final that's also up on Lon Kappa. And that's pretty much the plan. And if I know this finals week you have a tremendous, I know people are really stressed out and have a lot to do. So the other thing that I'm going to post is a grade calculator if you haven't already seen it yet. It's the same one we used in Stat 100, where now that you know pretty much all your grades, except it, you can get your homework in, you can finish up all the bonus. You're going to get, for both classes, you'll get points if you turn in the notebook, right? You'll get bonus points both for the online class, and you're just going to go to the final, and you'll turn in your filled-in notebook, and you can have all the pages. You must have all the pages filled in, except and you're allowed 3 blanks. Everything we covered in class. If we didn't cover it in class, you don't have to fill it in. I'll send out more explicit instructions, but if your notebook has a lot of missing pages, this might be a good time to fill it in if you need those bonus points. And I'll post a grade calculator. You can put all that in and see what you need to get on the final to achieve whatever grade you're aiming for. So I'll send that out to you soon, and have fun studying, and I'll see you next time.